So this is the recording of magnetism. In magnetism, I'll just tell you that what are the properties of the magnet. The properties of the magnet, when freely suspended, comes to rest in north-south direction. When cut into pieces, still exhibit polarity. Even when cut into pieces, it will have polarity, south pole and north pole. And then keep a magnet and keep a pin here. This is north pole and south pole. This will behave like a south pole, and the pin will acquire a south pole nearby. That's the reason it's attracting. The magnetic induction. Magnetic induction is preceding attraction. Even before it attracts, the induction is happening, inducing a magnetic field. This. So the magnetic induction precedes attraction. So what are the 3 points? The first point is, when freely suspended, comes to rest in north-south direction. When cut into pieces, exhibit polarity. And the third point is, magnetic induction precedes attraction. These are the properties of magnet. The second one is properties of the magnetic field line. Outside, this is north pole and this is south pole. Outside the bar magnet goes from south to north. Within the bar magnet goes from south to north, north to south. And within the bar magnet goes from south to north. Outside the bar magnet goes from north to south. Within the bar magnet goes from south to north. Thereby, what's happening is, within the bar magnet it goes like this, and then it goes like this, and so then within the bar magnet it's uniform magnetic field. Okay, so what are the properties? And they form a closed loop. Can you see they're forming a closed loop always, unlike an electrostatics where it's not forming a closed loop. So then what are the properties? Outside the bar magnet, the magnetic field lines property. Outside the bar magnet they go from north to south. Within the bar magnet they go from south to north, and the degree of closeness indicates the strength of the magnetic field. And then next point we can say is no two lines will cross each other. If it does, it indicates two directions at one point, which is not possible. And they always form a closed loop. Field lines always form a closed loop in magnetic field lines. Okay, so these are the properties of magnetic field line. And you can see a uniform magnetic field within the magnet, uniform magnetic field. So the next is the third thing that I want to teach you is about what is the magnetic axis. And line joining a north pole and the south pole passing through center is known as axis of a magnet, or a magnetic axis. What's about magnetic meridian? A magnetic meridian is a vertical plane. Can you see like this? Passing through the magnetic axis is known as magnetic meridian. So then next is, I also want to teach you what is a magnetic dipole moment. When you have a south pole and a north pole, that's equivalent to minus q and a plus q in a dipole. This is called a magnetic dipole. This is called an electric dipole. So then you know that dipole moment is from negative to positive. Similarly, the magnetic moment is always from south to north. And you know that within the magnet it's always from south to north. Now a dipole moment is P, which is either of the charge into 2A. But here the magnetic moment is M, which is either of the pole strength. There is no charge here, right? It's pole strength small m into 2L. Where instead of 2A that we studied in that lesson electrostatics, it's 2L is the total length, and either of the pole strength into 2L. This is a vector. Magnetic moment is a vector because 2L is a vector in. This is known as magnetic dipole moment. A magnetic dipole moment or a magnetic moment. From previous lesson, you know magnetic moment is also Nia, where n is number of turns. You can ignore it. Ampere meter square is the SI unit of magnetic moment. So it's this is ampere meter square. SI unit of pole strength you don't know. This is meter. The meter and meter square get cancelled. Thus you get the pole strength SI unit to be ampere meter. So magnetic dipole moment SI unit is ampere meter square. The pole strength small m. This is capital M and it's a vector. Pole strength small m. Small m is SI unit is ampere meter. And what else you can say? So next is take a magnet. You're trying to find a magnetic field. This is south pole and this is north pole. You're trying to find a magnetic field at any point P, which is at a position vector R. From the center of the magnet, you know this is L and this is L. So this distance is R minus L, and this distance will be R plus L. And just like electrostatics, the north pole outside of the bar magnet is going to be emanating, so then its En is like this and Es is like this. It's Bn and Bs. It's magnetic field, and so Bn minus Bs is all you need, and it's mu naught by 4 pi into moment m. Instead of charge is 1 by 4 pi epsilon naught equal mu naught by 4 pi. Charge equal, instead of charge is pole strength m by r minus L the whole square due to this north pole, minus mu naught by 4 pi into small m by r plus L the whole square, and so mu naught by 4 pi into m is common. 1 by r minus L the whole square minus 1 by r plus L the whole square. So then LCM therefore is r square minus L square the whole square, which is 4rl, and so mu naught by 4 pi into m into 4r into L by r square minus L square the whole square is the magnetic field along an axial line. And you know that one of the pole strength 1, 2 and 1n, 2m into 2l is capital M, so it will become mu naught by 4 pi into 2 capital M by r square minus L square the whole square, whereas r is much larger than L. It will be mu naught by 4 pi into 2 capital, sorry, there will be one more r here, okay, is 2m by r cube will be the formula for B axial. Then it's about the positive direction. It's on the positive direction of x-axis, or what you say, you know, generally it's like that, no? The resultant magnetic field will be like this, because north pole will have a more effect on this point. So next is equatorial line. Equatorial line is here at any point P, which is at distance r. You know, this side is L, this side is L, and so then you know this is going to be emanating from the north pole, and it's going to be like this. South pole, it's Bs and Bn. And you know the resultant is like this, and this is theta, this is theta, this will be theta, theta. So you'll have a Bn cos theta and a Bn sin theta, and similarly you will have a Bs cos theta and a Bs sin theta, a Bs sin theta which is vertical. Okay, because of this component you will have like this and like this. So this is vertical component is getting cancelled, the horizontal component is getting added, and this distance is L, and this distance is root of r square plus L square, and so then you know that it's Bn cos theta plus Bs cos theta, and B and B are having the same value, mu naught by 4 pi into a pole strength by a distance root of r square plus L square the whole square. Root and square get cancelled, which has to be multiplied by 2 times because both of them are the same value. And cos theta in general is adjacent by hypotenuse, which is L by r root of r square plus L square. So then the top will be mu naught by 4 pi into capital M by r square plus L square whole to the power 3 by 2, where r is much larger than L. It will be mu naught by 4 pi into M by r cube, and that is along with the magnetic field along an equatorial line, and it's going to be along negative x direction, considering this was from north to south, okay, and ns direction. And so then you know that the axial and equatorial are anti-parallel to each other. Axial is 2 times the equatorial, and all this you know. And so let's go to next, because you've learned it already in that lesson. Now there is a uniform magnetic field in which I am placing a bar magnet, and that's like a dipole, magnetic dipole of length 2L, and this is M1 and this is M2, making an angle theta, and you know that opposite side is 2L sin theta. You know, to experience a torque is equal to force into perpendicular distance, and force is normally, right, E is equal to F by Q, F is equal to E into Q. In this lesson, it's magnetic field into pole strength small m, B small m into 2L sin theta, and 2L m itself is capital M, it's B capital M sin theta, which will become torque is equal to M cross B, and so torque will be maximum when theta is 90 degree, and torque will be 0 when theta is 0, and so on. Let's draw potential energy is torque into d theta. Torque itself is mv sin theta d theta. On integrating both sides, the sin theta will become minus cos theta minus mb cos theta, integrated from theta 1 to theta 2. Upper limit minus lower limit is minus mb cos theta 2 minus cos theta 1, and a cos theta 1 is 90 degree, cos 90 is 0, cos theta 2 is theta. So then the potential energy itself is minus mb cos theta, and when theta is 0, the potential energy becomes minimum, it's minus mb. When theta is 180, the potential energy becomes maximum, which is plus mb. and the maximum potential energy stands for unstable equilibrium always, and this one stands for stable equilibrium when the potential is minimum. These are some things that you learnt in electrostatics, which is a replica of it. Now let's go to next one. Is about the lesson really starts here. The first one is a magnetic moment of a revolving electron in hydrogen atom. You know, hydrogen atom is H atom, where the nucleus is at center. The electron is going to be orbiting around in this direction. So then you know that there will be a moment, and that moment is what they are asking. I is equal to Q by T is I, and M is Ia near, but let's take the number of turns to be N. I is equal to Q by T, and A is pi r square. T is 2 pi r by V for the rotational motion. Pi r square, pi and pi get cancelled, r and r get cancelled. So magnetic moment itself is Q VR by 2. You can write VR to be L by M. Angular momentum is r times linear momentum. And can you see that you can write VR as L by M, Q by 2M into L vector with a negative sign is the magnetic moment. Why is the negative sign? If an electron is revolving in this direction, the conventional current will go in this direction. So you keep your curled, take your right hand thumb rule, keep your curled finger in the direction of the red arrow. The thumb, which is downward, will give you the direction of the magnetic moment. Magnetic moment and the area vector will be in the same direction. So you have to take the curled fingers in the direction of the red arrow, because conventional current direction is always opposite to the flow of electron. The conventional current direction, flow of here electron is flowing. When the magnetic moment is downward, the angular momentum is upward, and that's the reason you have a negative sign. If the electron was going in the clockwise direction, then you should consider conventional current to be flowing in the left direction. And so curled finger in the red direction shows that the magnetic moment is upward and the angular momentum will be downward. The magnetic moment will be upward because area also is upward. So I hope you understood how you use right hand thumb rule to determine the direction of the angular momentum, and hence linear momentum, and hence magnetic moment and angular momentum. Okay, so then that's about it. And then you can also, by chemistry, you know, magnetic moment is minus Q by 2M into NH by 2 pi, angular momentum of a revolving electron of hydrogen atom, Bohr's postulate. So if H is equal to, N is equal to 1, the first octet of the hydrogen atom, minus Q H by 4 pi M will be is called Bohr's magneton. It's called Bohr's magnetron, not magneton, magnetron. Okay, it's a constant because all these values are charge of an electron, mass of an electron, Planck's constant. Bohr's magneton is a constant, and that's what is Bohr's magnetron? It's a magnetic moment of a revolving electron of the hydrogen atom in the first octet. Okay, so then these formulas you should be really clear, such as magnetic M is equal to QVR by 2, and you can also be written as minus Q by 2M into L. You can also write L as NH by 2 pi, and all these formulas you should be clear because they'll come in numericals. 100% they'll ask you numerical. So this is about hydrogen atom and an electron revolving and a magnetic moment. This is the formula you have to use to do all the numericals that comes your way. Okay, next is about a solenoid. You all know that the current carrying solenoid is like a bar magnet. You should imagine this to be a bar magnet. Okay, so I told you in a bar magnet, the magnetic field is going to be parallel to each other, uniform magnetic field. They'll ask you this question. In a solenoid, the magnetic field at the center is B. What can you say about the magnetic field at the end? It's B by 2. Why? Because they're parallel, but as it comes closer, it diverges. You know, like that. So because of this, the magnetic field strength comes down. That's a point that they'll ask you sometimes in a solenoid. A solenoid is always equivalent to, and within the solenoid, the magnetic field is always uniform. And you know, B is equal to mu naught into small n into I and all that. The quarter formula which we learned. Okay, so then that's about the solenoid. And next is I want to teach you in this lesson is about the various components of the earth. Is like, you know, earth is like a sphere. It's not exactly a sphere, it's flattened at the edges, you all know. But when you freely suspend a magnet, it always comes to rest in north-south direction, and this is called geographic axis. What we learn in geography? Geographic axis is how the compass needle is getting oriented when you freely suspend. Why is it getting suspended like this? You can imagine a buried magnet, deeply buried magnet under the earth, whose south pole is here, north pole is here. That is the reason this north pole is coming to attracted by this south pole. This is called magnetic axis. You are imagining a magnet which is buried deeply under the earth, but is there really a magnet? No, but there are ferromagnetic substance deeply buried in the molten form in the earth. And the surface of the earth has got charges, and when the earth spins, the charges are moving, which constitute a current and behaves like an electromagnet. So you can understand that definitely you can imagine something like a magnet. So we are imagining it to be a bar magnet with south pole on this side, because in day-to-day life, this is the north pole by the compass needle. So deep buried under the earth, you can imagine a south pole and a north pole like this. And this is magnetic axis, and that's geographic axis, and there's an angle between them. They don't exactly coincide. I don't have to know why, just leave it like that. What is straight in here, I'm going to draw the meridian which is slanting here, and what is red which is slanting, I'm going to draw it straight here. This is the meridian, this is the geographic meridian, and this is the magnetic meridian. And it's like a notebook, so there'll be a resultant magnetic field which goes through the notebook like a parallelogram law, and that B will have a BH and a BV, and this angle is called delta or dip angle. This angle between this theta which transcends here in the meridian also, this is called angle of declination. Angle of declination. This is called angle of dip or dip angle. This is called resultant magnetic field. This is called horizontal component of the Earth's magnetic field. So various components, very important is theta is the angle of declination, delta is the angle of dip, and BH is the horizontal component of the Earth's magnetic field. Horizontal component of the Earth's magnetic field. So these are the various things you should know. Okay, now I'll tell you what is this dip meaning, okay, just for you to face the entrance exam. That's not even there in the portions, but however I have to teach you what does a dip mean. So deeply buried under the earth, there is a magnet whose south pole is here, north pole is here. The magnetic field lines go outside the north and go towards, so outside of the bar magnet goes from north to south, within the bar magnet goes. This is the dip needle. This is the dip needle. Can you see this dip needle? And this is the horizontal component of the Earth's magnetic field, which is basically the surface of the Earth. They are making an angle theta. Can you see? There's a vertical component and a horizontal component of this dip angle. This dip needle has a vertical horizontal component. The horizontal component is along the surface. This angle is called delta dip angle. Therefore, at the equator, the dip angle will be parallel to the surface of the Earth. The dip angle will be 0. At the pole, the dip angle will be perpendicular to the Earth's surface, and so then therefore the dip angle is 90 degree, and therefore there are no components at the equator, because the horizontal it's already, there's only horizontal which exists. It's always parallel to the magnetic field. There's no components. So then that you understand, and let's go to the next question. Next thing that I taught you in today's class is about the various terminologies, such as what is B, what is H, what is I, what is susceptibility. Okay, let's come to B. B is the magnetic field strength, which can also be called magnetic induction. You always remember B to be Tesla. A Tesla itself is Weber per meter square, which shows that flux passing through unit area. That is what is B. But however, I don't want this explanation. According to Curie, B is proportional to H. B is equal to mu into H, or B is equal to mu naught into mu R into H. The permeability of any medium is absolute permeability into relative permeability into H. Okay, this is first thing that you should know. Of course, the SI unit stands the same, but a different way of looking at the definitions. What is H? H is the field related. It's called magnetic intensity. magnetic intensity. This is called intensity of magnetization. Intensity of magnetization. Magnetization. This is specimen related, and this is field related. You know, you have a magnetic field, the strength of the field will be different. You place a specimen, the ability to get magnetized can be different for copper, for silver. So there are two different things. One is field related and specimen related. And this, another name for magnetic intensity is ampere turns. Ampere turns, which is current into number of turns. Current into number of turns, but per unit length actually. Per unit length, that's why it's ampere per meter. Though they don't say it in the definition, it's ampere turns, which is ampere current into number of turns per unit length. But unit length, so you can ignore L. But in the unit, you can't ignore. Intensity of magnetization is moment acquired per unit volume. Moment acquired per unit volume. That will also be ampere per meter only. Susceptibility is ratio of I by H. In order to remember H is going to come down, you can sneeze and see H. H will always come down, your head is going down, so I by H. So that's another formula. Then you should also know that when you have a field, you place a specimen, the total magnetic field is because of BH and as well as I. The field and the specimen related, which is mu naught into H plus mu naught into I, which is mu into H or mu into H, which will be, you can divide the whole thing by H. The whole thing by H and H. So you get mu is equal to mu naught plus mu naught into I by H is susceptibility. Mu naught can be taken out and you can write 1 plus susceptibility. Mu by mu naught itself is mu r, which is 1 plus susceptibility. Mu r is equal to 1 plus susceptibility. Very, very important. If you know the susceptibility, you can form the relative permeability. So these are the formulas and things that you have to memorize. There's no way that you can understand it. It's all definitions only. So this relationship is very, very important. Next is I'm going to teach you the difference between dia, para and ferro. A diamagnetic substance, a paramagnetic substance and a ferromagnetic substance. So next is about the difference between dia, para and ferro. Dia, para and ferromagnetic substance. Okay, hope it's recording. Yeah, diamagnetic substance. When suspend a specimen, a specimen in the magnetic field, a diamagnetic will come to rest in a perpendicular to the magnetic field. When you suspend a paramagnetic material, suspending a paramagnetic material, it will align itself in the same direction as the magnetic field. A ferromagnetic also will align itself in the same direction. This is about suspending. The second one is about placing. When you place a diamagnetic specimen in a magnetic field, it will get inside of it. The inside, it will be oppositely magnetized, weakly magnetized in the opposite direction. When you place a paramagnetic substance in the magnetic field, within the specimen, it will get weakly magnetized in the same direction. Weakly, again, weakly magnetized in the same direction. This is opposite direction. Ferromagnetic is just a stronger version. It will get strongly magnetized in the same direction. Okay. So then next is about again, when you place a diamagnetic specimen, what will happen to the external magnetic field? That's getting expelled. Whereas in the paramagnetic specimen, it's getting contracted like this. In a ferromagnetic substance, so many field lines will go through. So that's the variation. This is about what is happening to the magnetic field around it. This is about what is happening to the specimen's field. Okay, so the next is the fourth point. Diamagnetic moves from stronger to weaker field. So if you place a north pole and a south pole closer together, you know the field is strong and it's very weak. And a molten magnetic material moves from stronger to weaker. Whereas you move the magnet away and you place a china dish here it is going to be stronger and here it's going to be weaker. This is how it's going to behave. And this is how dia is going to behave. Therefore, para is the opposite of it. Okay, so you can understand the para is going to move from weaker to stronger. So in the first case, it will be convex like this and a concave like this. And when the magnets are closer, and when the magnets are far away, it's going to be moving from weaker to stronger, so it's going to be like this in here, and flat portion here. So that's the way ferro will also behave, because para and ferro are more or less same. So fifth one is about susceptibility. Mu r is equal to 1 plus susceptibility, and susceptibility is slightly negative, susceptibility is slightly positive, but susceptibility is very, very large positive value. Therefore permeability is slightly less than 1. Permeability is slightly greater than 1. And permeability is relative permeability is much greater than 1, like 1000, 2000 and all will be the value of relative permeability for a ferromagnetic substance. Okay, so next point is about a diamagnetic do not obey Curie temperature. Susceptibility versus temperature graph is a constant. Susceptibility versus temperature is a reciprocal graph, and for this and this also is a reciprocal graph. So these are the points which you should know. And one more point I'll say, paramagnetic says para, but it's got unpaired electrons, whereas diamagnetic has got paired electrons. The fact that dia has got paired electrons, the net moment will be 0. Net moment is always 0. Why? Because the spinning paired electron will spin in opposite orientation and the magnetic moment will get cancelled. Whereas unpaired electrons is there in para, so it will have a net magnetic moment will be there. Net magnetic moment will just be there in para. The examples of para, I'll tell you, nitrogen N2 is an example of dia. And N alone, if you see, is 7th element, which is 2, 5, which is 1s2, 2s2 and a 2p1. It's unpaired. You can't call it as para, never. Because N exists as N2 and exists only as dia. Nitrogen is a very good example. Other than that, anything which is gold, silver, copper, anything which is glittery, I'm giving you a clue, example of dia. Para is like sodium, magnesium, anything which has got unpaired electron. You can check out, physics better. Those are all the examples of para. Aluminium, examples of para. And ferromagnetic substance, the examples can be iron, nickel and cobalt. Iron, nickel and cobalt are the examples. Now the examples you should remember. And so let's go to, let's also, other than this, you can, if they ask you water or any other element, you see if it's got paired electrons or unpaired electrons, and based on that you can classify them as dia, para and ferro. And let's go to this, which is a ferromagnetic substance. Why is that? When you place a specimen inside a ferromagnetic substance inside gets strongly magnetized in the same direction, whereas a paramagnetic substance gets weakly magnetized in the same direction. The reason being that the orientation is slightly random, whereas here the orientation of every magnetic moment are in the same direction in every domain. A domain will have many electrons, like 10 to the power 11 atoms will be there. I think 10 to the power 35 atoms will be there. With so many electrons are there. The orientation of the magnetic moment are all in the same direction. So then therefore it's getting strongly magnetized, the specimen. Whereas here in the specimen, the orientation is slightly random, and so then they are getting weakly magnetized. In the ferromagnetic also, you can classify into a hard ferromagnetic substance and a soft ferromagnetic substance. Soft one is whatever I said, iron, nickel and cobalt, or simply the soft ferromagnetic substance. And a hard ferromagnetic substance is alnico, hard ferromagnetic, and then also a lodestone. A lodestone is what a compass needle is made up of. A compass needle is made up of lodestone and hard ferromagnetic substance. These are the things you should know. And then last is Gauss law. I'll tell you about integration of B dot ds is Gauss law is equal to 0. Why is it 0? In electric field, Gauss law is integration of ds is E dot ds is q by epsilon naught. But q can exist, one charge, but one pole cannot exist. Monopole does not exist. Monopole does not exist, and so such a case will become equal to 0. A surface integral of magnetic field over a closed loop is always equal to 0. That's Gauss law in magnetism. Okay, so next is I did 2 numericals. The 2 examples that was given in that textbook. I hope you can spot those numericals, very, very important. Then you have a magnetic needle, a P, which is placed at a point O. I will just roughly tell you the sum. You have to learn after that. So then they will give you, say at this point, they will give you a Q1 or a Q2, which is in this direction. This is a magnetic moment, M2, of some other magnet. A magnet is placed in a magnetic field. The magnetic field is a black color magnet, for which the magnetic field at this point will be equatorial line. And the moment the arrow mark is like this, this is south pole and this is north pole. You can convert this into a magnet itself. And at the equatorial line, it will be away from the north pole. So then this is the magnetic field B2 at this point due to this magnet, black color magnet. The magnetic moment and the magnetic field are making an angle 90 degree. And therefore, you can write what is the value of this B2 at this position, equatorial line, mu naught by 4 pi into 2 capital M by R cube. That is the magnetic field along M by R cube is the magnetic field along an equatorial line. Magnetic torque is equal to MB sine theta. M and B are making an angle 90 degree. Therefore, torque is maximum and it's MB. And that's about this position. They would have also given you another, say something like this. They would have given you a Q1 like this. Q1 or whatever value. That's a magnetic moment of some other electron, some other magnet, and you want to find the magnetic field due to this magnet. When North Pole says it's away from the North Pole, so then if it's, I think the Q1 will be given downward. The Q1 will be downward and the magnetic field B1 will be upward. It will be directed magnetic field due to the black color magnet will be upward axial line. It will be away from the North Pole and the angle itself is 180 degree. And therefore the torque will be 0, MB sine 0. Potential energy is minus, it will be minus MB cos 180. And cos 180 is minus 1. The potential energy therefore is maximum. And B's value is along the equatorial line, axial line, which is mu naught by 4 pi into M by R cube. 2M by R cube, 2 capital M by R cube because it's axial line. So you can say where it will be in stable equilibrium, where it will not be in stable equilibrium. This was one sum. You can refer to that sum and learn more about that numerical. Very, very important. There's no paper without that numerical. This question will always start with the compass needle placed at O. Okay, so next question that I saw today is they had given the relative permeability to be 400. They have given a solenoid which carries a current of 2 amps. They have given the number of turns per unit length to be 2000 per meter. But I would consider that's small n. So, but I would consider the whole sum to be per meter and take capital N itself is 2000. And now the question was to find what is H, what is I. They don't ask I because they don't want you to confuse yourself with the current. So then they changed I, which is actually here M, capital M, which is not current. It is intensity of magnetization. The specimen related intensity of magnetization, and H, which is the field related, and it's ampere turns. Ampere and number of turns, you can multiply both of that, you get 4000 ampere per meter to be the magnetic intensity. And then they ask you, you can find what is susceptibility. Susceptibility is I by H, and if you should find if you know susceptibility, you can find I because you can substitute H here, which is 4000, for which you should know susceptibility. To get susceptibility, what do I do? No, I'd rather find I do you know what is the value of susceptibility in this sum? So I can't use this method because I don't know susceptibility, and so then therefore to find I should write B is equal to I'll tell you how to find, B is equal to BH plus BI. What is B? B itself is proportional to H. B is equal to mu into H. B is equal to mu R into mu naught into H. So mu R into mu naught into H is B, which is equal to mu naught into H plus mu naught into I. Okay, they are asking about I. So mu naught throughout get cancelled. Mu R into H is equal to H plus I. So you can take the H to the other side. Mu R into H minus H is equal to I. Mu R has been given to be 400 or I think it was given to be 400. That was given in the question. So 400 into H can be taken into common, H into mu R minus 1. So 399 into H, which is 4000, is equal to I. and they have taken it as 400 only, and 4 4s is 16. I think this is a number of turns. I think number of turns was 1000 per meter. So then therefore this is also 1000. They took it as 400. So 400 into 3 zeros. So 399 into 1000. I just think they took it as 400 into 1000, which is 4 into 10 to the power 5. I don't know, the numericals, then the value could be different. Just make sure that plugging the right values, and I don't have the textbook with me. For this I find what is I. Once I find I can always find susceptibility, which is I by H. That is done. Then they'll ask me in that question, they'll ask me what is the magnetic current. Magnetization current is that current which is additionally passed into the solenoid, so that it produces the same magnetic field which was originally there even when the core has been removed. The core of the solenoid has been removed. So it's B is equal to mu naught into small n into I plus mu naught into small n into Im due to the additional current. So you know that B itself is here, from this formula you can plug in that B's value. Mu naught into small n into I, the respective values here also. And this, you can actually find the value of Im. You can take it, that's it, B is minus mu naught into small n into I by mu naught into n is equal to Im. So you can find Im using this. Very, very important sum. Okay, anyway, carry on. I hope you're clear.